Today I'll be talking about transformers. I'm going to talk about how they work and how you can choose one, and I'm primarily going to be talking about those transformers that change line voltages into low voltages that you might use for your projects, for example. In a future video I'll be talking about audio transformers, but today I'm mostly going to be talking about line voltages. So let's get started by looking at how transformers work and how you can choose them. So first I'm going to talk about magnets and the difference between flux, flux density, and flux linkage, because these concepts are important for understanding how a transformer works. So let's start with flux. Let's say that we have a horseshoe magnet with a north pole at the top and a south pole at the bottom. We know from our everyday experiences with magnets that the magnetic field is strong right between these two pole faces, and I can represent that magnetic field by drawing lines connecting the North Pole to the South Pole. The field will fringe out a little bit at the sides, and that's also indicative of our daily experiences with magnets. The field gets weaker, it fringes out. The field is still there, but it's just not as strong as it is if you're right in between the North and the South Poles. These lines that I'm drawing here are called flux lines, and if you've ever done an experiment in elementary school where you've taken a sheet of paper, sprinkled some iron filings on it, and then put a magnet below the paper, you've noticed that the iron filings align themselves with these invisible lines of force, which I'm now calling flux lines. Flux lines are not always straight. It really depends on the geometry of the particular magnet that you're working with. In a horseshoe magnet, the North Pole and the South Pole are facing each other, but in a bar magnet, they're on opposite sides of an iron bar. The flux lines then have more of a curved shape that connect the two poles. Of course, in reality, these flux lines ought to be symmetric about the center of the magnet, but my drawing isn't quite accurate here. I think you get the idea of what a flux line is, though. Of course, flux lines can also occur with an electromagnet. It doesn't have to be a permanent magnet. Here I have an example of a bar of iron around which we've wrapped several turns of wires. If the current is passing in the direction shown, then we'll have effectively a north pole created at the top of the bar of iron and a south pole created at the bottom of the bar. I can use the right hand rule in order to determine the direction of the magnetic field. If I wrap my fingers in the direction of the flow of current, then my thumb will point towards the north pole of this magnet. If the direction of current were to change in this particular configuration, then the south pole would be at the top and the north pole would then be at the bottom. Of course, with such an electromagnet, we're also going to get flux lines that connect the north to the south pole, just as we would with a permanent magnet. The only difference here with the electromagnet is that the strength of the magnetic field can be adjusted. It's a function of the current going through the wire. More current means a stronger magnetic field. Let's now discuss in a more mathematical way exactly what flux means, or exactly what it means for a magnetic field to be stronger in one case than another. Flux is defined as the amount of magnetic field passing through a particular surface. We're going to use the capital symbol phi to describe flux, and the unit that we're going to use is Webers. To illustrate what flux means, I'm going to draw two surfaces, and we're going to draw a situation that has more flux and a situation with less flux. You could think about flux as just being a count, the number of lines that are passing through a particular surface. I've not said explicitly that it's the same surface, and that's one of the problems with flux, is that you don't necessarily know whether a magnet is more powerful than another magnet if you're just comparing flux, because it really depends on the particular surface through which these flux lines are passing. What makes a lot more sense is the concentration of these field lines. How many field lines are there through a particular surface in one magnet versus how many field lines pass through that same surface area in another magnet. This brings us to flux density. Flux density can be defined as how concentrated these magnetic field lines are. We use the symbol B to describe the flux density, and it has the units of Webers per square meter, or Teslas. When we think about magnets, it's usually Teslas that are used in order to describe how strong a magnet is. A very strong magnet could have a field measured in single-digit Teslas. For example, the magnets that were used in the Large Hadron Collider at CERN in Geneva typically had field strengths around 7 Tesla, and these are incredibly strong dipole magnets. Magnetic fields that we encounter in our daily lives are much less strong than this. Here we can see the difference between fewer field lines passing through a particular surface or more field lines passing through the same surface. The situation here on the right has a greater flux density because the field lines are simply more concentrated. We can go back here to our diagram and define the surface area that we're referring to as A. And just for the sake of argument here, I'm going to assume that it's the same surface area we're talking about in both of these situations. We can then see over here that our situation with more flux also has a greater flux density than our situation here on the left. We can define flux in terms of flux density. Flux is just flux density times surface area. I now want to describe something called flux linkage, which is a really important concept when it comes to electromagnets and transformers, which is what we're going to talk about here in a moment. Flux linkage is the flux enclosed by a loop of wire, and it also has units of Webers, but because the same wire can wrap multiple times around the same flux lines, it has a slightly different definition. We'll use the symbol lambda to describe flux linkage. Here we have a single loop of wire enclosing some lines of flux. That loop of wire creates a particular surface area with which we can define a magnetic field density. In this case, because the wire only loops around the flux lines once, flux linkage equals flux. The surface area is the area enclosed by the loop of wire. I now want to consider the same lines of flux, but I want the wire to loop around those same lines of flux twice rather than once. In this case, the flux is the same, but the flux linkage is now twice what it was before, and that really shows the difference between flux and flux linkage. In this case, there were two loops, so the flux linkage is twice the flux. But in general, if I had N loops of wire surrounding the same lines of flux, then my flux linkage would be N times the flux. Of course, we know from our childhood experiences about wrapping wires around pieces of metal and forming electromagnets that there is an intimate relationship between the current passing through that wire, the flux linkage, and the voltage that one puts across that wire. If you've had a class in electromagnetics, then you will have heard of Faraday's law before. But if you haven't, no problem. I'm just going to show what it is right now, and then we're going to use that result very quickly in order to show how voltages on the primary side of a transformer can be mathematically related to voltages on the secondary side of the transformer. If you're not familiar with calculus or derivatives, that's okay, because you'll still be able to understand the results in just a moment. So this is here for those students that might want to have a more intimate mathematical understanding. Faraday's law says that the voltage which shows up across a wire is related to the time derivative of the flux linkage. In an inductor, the flux linkage is defined as the inductance times the current, and that immediately leads us to the law of an inductor, which relates voltage to current. If you've seen Faraday's law before, sometimes you would see a minus sign before this derivative. The reason the minus sign is there is because it depends on the direction that current is defined going through that wire. So if current is defined going one way, then you won't have a minus sign, and if you draw the current with the arrow pointed in the other direction, then you'll find a minus sign. It's nothing to worry about. Because voltage is related to flux linkage, it gives us a way to change one voltage to another, with the caveat that you can only transform AC voltages, and that's clear here from the time derivative. If you use DC voltages, you're going to wind up with static magnetic fields. Furthermore, if the flux linkage, lambda, is not changing with respect to time, then the voltage just winds up to be zero. Let's now draw out what a typical transformer might look like and derive the relationship between voltages on the primary side to voltages on the secondary side. Let's say that over here on the primary side of our transformer, we have a coil of wire surrounding a bunch of flux lines. Assume that we apply voltage V1 to this coil of wire, then there'll be a certain current, I1, which passes through the wire, which then induces a flux linkage of lambda 1, which I'm depicting here with the red lines. I'm eventually going to say that the voltage is sinusoidal and that the current is sinusoidal. So let's first consider what happens if the flux is sinusoidal. If it's sinusoidal, then it will have a certain amplitude, which I'm going to denote by phi with a subscript m here referring to the maximum value or the amplitude of the sine wave. The flux linkage here on the primary side will be related to the total flux by a factor of N1. Let's go ahead and substitute for our flux and then use Faraday's law in order to find the expression for the voltage V1. Okay, that's Faraday's law. Notice here that the voltage is sinusoidal as well, and the amplitude of that sine wave is N1 times phi times omega. This is the amplitude of the voltage, or in other words, the maximum voltage at the primary side. Let's now assume that we have another coil over here that I'm going to call the secondary, and this coil surrounds the same amount of flux as it did on the primary side. We can again define the voltage, the current, the flux linkage, and the number of turns here on the secondary. I'm going to assume that the flux is the same. Now, why can I make this assumption? Well, the only way to assume that the flux is the same on the primary and the secondary side is to make sure that all the flux lines connect. Now, the best way of doing that, or the easiest way of doing that, is to insert iron into the core of the transformer and have the same loop of iron pass through both the primary and the secondary. The reason why iron or ferromagnetic materials are often used as transformer cores is because the flux lines really like to stay inside the iron. Iron has a much larger magnetic permeability than air, for example. So all of the big transformers that you'll find industrially often have iron cores. The flux lines stay nice and concentrated in the iron. You don't want flux lines to leak off and fringe out into the air, for example. The square shape of the red flux lines here then is exactly the shape of the core of this particular transformer. If you were to use air instead of iron, then you would have some flux lines passing through the primary side that just trail off into the air and never make it over to the secondary side. That would represent a loss in the transformer, and that's normally something that we want to avoid. That's why transformers usually use iron. But you cannot use iron if the frequency is too high, and there are a few reasons for that. Iron contains dipoles. Iron has hysteresis, meaning that if you have a very high frequency in your primary side, then the magnetic field will flop back and forth, or the polarity will change very rapidly. In a sense, hysteresis means the iron can't keep up with you. It can't flip and flop internally as fast as the magnetic field can, and then you have losses because of the iron. So when the frequency starts to get high, it makes more sense to use other materials, and if the frequency is high enough, it makes a lot of sense just to use air, because you can actually get less loss from the field fringing and the magnetic permeability than you would if you'd use an iron core. Let's continue in our derivation by assuming that all of the flux that passed here through the primary side makes it over to the secondary side. The flux linkage here on the secondary side, however, will be different from that on the primary because we might have a different number of turns. We can again use Faraday's law to calculate the voltage here at the secondary. We now have an expression for the maximum voltage at the secondary side. Let's make some observations about what we've calculated here. My first observation when comparing the primary side voltage to the secondary side voltage is that they're in phase with one another. When the primary side swings up, the secondary side swings up as well. The second observation that I can make is that if I take the ratio of these two voltages, I find that it's just N2 over N1. And that's probably the most important relationship when it comes to transformers, and that's what allows us to change AC voltages from high to low and vice versa. We can just use a different number of turns on the primary or the secondary side. If I call the maximum voltage or the amplitude on either the primary or the secondary Vmax, then I can see it's related to the number of turns, the flux, and the frequency. I'm going to write out omega as 2 pi f to make this really clear. Because of this concept of magnetic permeability, it's difficult for some materials to have a huge field concentration within them. In other words, there's usually a maximum phi that a particular material can handle well. From this expression, we can see that the maximum voltage is not only related to the turns ratio, or the number of turns in, but it's also related to the frequency. If we want to hold the voltage constant, then as the frequency gets lower and lower, we're going to be needing more turns in on the transformer in order to be able to accommodate it. What this means practically is that transformers that have been designed for use at high frequencies will have fewer turns than transformers that have been designed to operate at low frequencies. I have several examples here of transformers in front of me. All of these transformers were designed to operate at relatively low frequencies, so they tend to have large numbers of turns. This little blue transformer here is a PCB mount transformer, and you can see that here on the back it has relatively short leads that have been designed for mounting down to a printed circuit board. This transformer here is called a chassis mount transformer. You can see that it has two holes that you could put screws through in order to mount this down to an enclosure, for example. This slightly larger transformer here is called a toroidal transformer. It has kind of a donut shape to it. These transformers tend to be really efficient, and the reason for that is because the flux lines can stay concentrated relatively easily inside the donut compared to these other transformers here that might have a more squarish shape inside their enclosures. You might notice here that this transformer has more than 4 wires going into it, and the reason for that is because it has a few different taps into the primary and the secondary, so it's possible to achieve multiple voltages without redesigning the particular transformer. This can be mounted down by using just a single screw. It comes here with some pads. They have a hole into it, and the transformer came with a single bolt. So these are usually mounted down by just running the bolt right down through the center of the transformer. It has a nut on the other side to hold it down into an enclosure. The other transformer I have here is an audio transformer, and I would have a future video where I look at audio transformers in more detail. But the one thing that you might notice is that it has, again, multiple taps at both the primary and the secondary side. Let's look at the data sheets for some of these transformers. We'll start off here with the PCB mount transformer. This particular transformer has an input voltage of 230 volts, an output voltage of 12 volts, and I'd like you to notice that the efficiency reported here on the data sheet is 57%. You might also here notice on the power that instead of being expressed in watts, the power is expressed in volt amperes, and the reason for that is because the transformer ideally is not really burning up any power at all. It's just moving power from the primary to the secondary. And in order to express that without any confusion, that transferring of power typically has units of volt amps rather than watts. That's why here on the data sheet, the no load loss is typically 1 watt. The unit here being watt because the loss is inside the transformer itself. We can see that the frequency range for this particular transformer is at our line frequency. The purpose of this transformer then is to design power supplies. It transfers the 230 volts that one might find as line voltage into 12 volts here on the secondary side. Let's take a look at the data sheet for this toroidal transformer here and see what differences we can take note of. The particular transformer I have here is model 18, meaning on the secondary side we should have 18 volts, and on the primary side is our line voltage, which is 230 volts. We have multiple taps here on the primary side, so if, for instance, I were to tie these two taps together, then I could put in 230 volts across these two leads right here. And then on the secondary side, I could get 18 volts here, 18 volts here, or if I were to tie these two leads together, then I would get 36 volts. Notice that the efficiency for this transformer at 85% is significantly higher than the efficiency we saw with that PCB mounted transformer. And that's very typical of toroidal transformers. They've been designed to be highly efficient and highly reliable. Now the data sheet for this chassis mount transformer right here tells us that we should have 240 volts at the primary, 12 volts at the secondary, and the max output is 3 volt amperes. These kinds of transformers are often used to make power supplies, so we would typically measure a voltage higher than 12 volts over at the secondary side. It might later be 12 volts after we clean up the signal, convert it to DC, etc. One thing about this particular data sheet is that I don't see the efficiency mentioned. We're going to measure the efficiency over the bench here in just a moment. I don't expect the efficiency to be as good as that of the toroidal transformer, so it'll be interesting to see how efficient this particular transformer is. This is what the circuit looks like that we're going to use to test it. I'm going to plug the primary side of this transformer into the wall. Here in Singapore, we get 230 volts RMS from our mains. I don't want to accidentally start a fire or run too much current through the primary side of our transformer, so I'm going to install a fuse. I'll be using a 10 milliamp fuse here on the primary side. the presence of that 10 milliamp fuse will limit the power passing through my transformer to 2.3 volt amperes. That puts us below the maximum power that this transformer can handle according to the data sheet and should keep us safe. On the secondary side, I'll be using a 100 ohm resistor. Our expected output power is the voltage at the secondary squared divided by our resistance. Our expected output power here is about 1.44 watts. I've chosen a resistor that can handle up to 5 watts passing through it, so we won't have any problem of starting a fire over on the secondary side either. Even if the output power of this transformer is a little bit higher than what I expect, the resistor should still be able to handle it safely. I want to describe my testing plan for finding the efficiency of this transformer. I'm going to be measuring the current passing through the primary side and the secondary side simultaneously. Efficiency will be defined as power out divided by power in. If the transformer is perfect, then these powers should be identical to one another, but we know that that's not going to be the case. Output power will be I2 squared times R, and I2 will be directly measured. Our input voltage is 230 volts, and I'm going to neglect the voltage drop across the fuse. We know that our resistance is 100 ohms. We have enough information from just the measurement of two currents in order to find the transformer efficiency. Let's go over and do that at the bench right now. We are going to be working here with line voltages, so we do need to be a little bit cautious about the safety. I have a UK style plug here. It's 3-prong plugged, and we have 3 different colors of wires here coming out of the cable. Brown refers to the hot, blue the neutral, and then we have the earth ground, which is striped green and yellow. To connect to the primary side of the transformer, I'm only going to be using the hot and the neutral. We're not going to plug it in until everything is wired up here for safety considerations. I'm going to wire up the primary side of the circuit first, and I'm going to make sure that the fuse sits on the hot side of the circuit rather than the neutral side. We'll be using this ammeter here to measure the current on the primary side. For the moment, I have the secondary side without any load attached to it. We have this multimeter set up to measure AC volts, and we have this one at the primary side set to measure the current draw. So we're going to see how much current the transformer draws when we don't have any load attached to it at all. So now we're going to put out a warning sign to indicate that we have a relatively dangerous setup here. I'm going to go ahead and plug it in and turn it on. So what I notice here is that we have about 6 milliamps of draw here on the primary side at 230 volts. And here on the secondary side, we have about 13.19 volts. Now keep in mind, our secondary side is not attached to any load at all. So we have some power being used up here in the transformer. We can multiply 6 milliamps times 230 volts, and we find out that the transformer is consuming 1.38 watts without anything attached to the load. That means that at the moment, the transformer is 0% efficient because power out divided by power in is 0. But that's not really very fair to the transformer. We need to attach it to a realistic load and then see what the efficiency is. I'm going to go ahead and turn it off, unplug it, and attach up a 100 ohm load to the secondary side. We now have this multimeter set to measure current on the secondary side as it's connected to a 100 ohm load. I'm going to go ahead and plug it in, turn it on, and let's see how much current is flowing both on the primary and the secondary side of the transformer with the load attached. So it looks like we have about 8.97 milliamps at the primary side and 104.7 milliamps at the secondary side. So from these two currents, we can find the efficiency of the transformer. Let's start with the secondary side. We have 104.7 milliamps, so I can take I squared times R, which is 100 ohms, and find out that on the secondary side, we're consuming 1.1 watts of power. Let's see how much power we're putting into the transformer on the primary side. That would be I times V, where the current here is 8.97 milliamps, and we have 230 volts. So that works out to be 2.06 watts. So if we take the power delivered to the load, which was 1.1 watts, and divide it by the power which was supplied to the primary side, which is 2.06 watts, we find that the transformer is 53.4% efficient. As you might have noticed, the efficiency of this chassis mount transformer was not as good as what a toroidal transformer would hypothetically be. Let's now go back over to the tablet computer and work a few examples related to transformers. In example 1, a transformer had 1,000 turns on the primary side and 100 turns on the secondary. Is this more likely a low-frequency transformer or a high-frequency transformer? Well, first of all, we can already see that the purpose of this transformer is to change a high voltage on the primary to a low voltage on the secondary. These numbers of turns indicate to me that the transformer is probably going to be used at low frequencies. To see why, let's recall our expression for the maximum voltage in a transformer. At a given voltage and a given flux, the only two variables in this equation are really N and F. They're multiplied times one another. So when I see that the number of turns is high, it tells me that the frequency is probably low, because if the number of turns were lower, then the frequency would probably be higher. What happens if you take a transformer that doesn't have enough turns on it and you try to operate at a low frequency? Well, what you'll find is that the transformer starts to become less and less efficient. That's what happens. So when I see in this problem that a transformer has a certain number of turns, I'm implicitly assuming that it's been well designed. Example 2, a transformer had a ferrite core rather than an air core. Is this more likely a low-frequency transformer or a high-frequency transformer? The answer is low frequency. If we rearrange this expression a little bit and we fix everything on the left-hand side, we can see that the maximum allowable voltage in a transformer is related to the maximum flux times the frequency. I know that iron cores can handle more flux compared to air. So if phi is high, then that transformer was probably designed for low frequencies. Anytime you see a transformer where the core is air, or anytime where the wire is not very tightly wrapped around something, then it's an indication that that's a high-frequency transformer. Let's take a look at one more example. In example 3, a transformer had 1,000 turns on the primary side, 100 turns on the secondary, and was attached to the mains at 50 Hertz. We're going to calculate a few things about the transformer given that the cross-section is 10 centimeters by 10 centimeters. This is a relatively large transformer, and I can see from the turns ratio that its purpose is to change from high voltage to low voltage. We know that the voltage at the secondary is related to the voltage at the primary by the turns. The voltage here could refer either to the max or to the RMS as long as we're consistent. Rearranging this expression and plugging in numbers from the problem tells us the voltage at the secondary side should be 23 volts RMS. We're going to now find the maximum flux in the core, and I'm going to use the primary side voltage to calculate it. You can use the secondary side alternatively, it doesn't matter. We've earlier derived an expression for the maximum voltage at the primary side. I'm going to use this expression substituting 2 pi f for omega. We're looking for exactly this quantity, the maximum flux. So let's solve this expression for that. This expression contains the maximum voltage, or the amplitude, but what I'm given in the problem is the RMS voltage. So let's convert the maximum voltage to the RMS voltage. They differ by a factor of the square root of 2. I can now substitute in for the voltage, the frequency, and the number of turns from the problem. The flux in the core of this transformer is 10.4 milliwebers. In part C, we're asked for the maximum flux density. Flux is related to flux density by the surface area, so it's relatively straightforward here to solve for B, giving us 1.04 Webers per square meter, or equivalently 1.04 Teslas. In this video, we've primarily looked at low voltage transformers whose function is to convert mains voltage into voltage that's appropriate for small electronics devices. In the next video, we'll be looking at audio transformers in more detail. This video is part of an organized sequence where I explore various AC and switching circuits. If you enjoyed it, then you might consider following the channel's playlist to learn more about these types of circuits.